How big does something in the universe have to be before the word big basically stops being useful to you? Let's build this up in simple steps with real numbers and see where your sense of scale breaks. You live on Earth, a planet about 8,000 miles across, around 13,000 kilometers. Your planet orbits the Sun, which is one star out of the hundreds of billions inside the Milky Way, a disk of stars about 100,000 light-years wide. 1 light-year is about 6 trillion miles, around 10 trillion kilometers, so that disk is roughly 600 quadrillion miles across, around 950 quadrillion kilometers. That whole structure, the entire Milky Way, is what most people imagine when they hear our galaxy. Now, stretch your mind one step further. Astronomers have found systems that make even the Milky Way look modest. One of them is called IC 1101, and in many definitions, this galaxy is one of the biggest single galaxies we know about. Instead of 100,000 light-years, its main body stretches to at least several 100,000 light-years, and when you include the very faint outer regions, some measurements put its total span at 4 to 6 million light-years from one side to the other. Its extended halo alone can be traced to about 2 million light-years from the center. That is not a guess or a casual exaggeration. Those distances come from direct measurements of how its light profile fades with radius and how far we can still statistically detect its stars above the background. The next question is, how far away do you have to go in the universe to actually find something like this? This galaxy sits roughly 1 to 1.1 billion light-years away, in the direction of the constellation Virgo. That means the light reaching us left around 1 billion years ago. In miles, its light has traveled about 6 sextillion miles, around 10 sextillion kilometers. That number is so large that it is almost impossible to picture. What matters for you is this. When you talk about this galaxy, you're talking about an object that is both physically huge and extremely distant, and yet still bright enough for us to measure and study with modern telescopes. We know this distance in a precise way. When astronomers split its light into a spectrum, they see that all the familiar lines from elements like hydrogen and oxygen are shifted toward the red. This red shift is about 0.077. In simple terms, the universe has expanded while the light from this galaxy was on the way to us, stretching the wavelength. Using the current value of the Hubble constant, that redshift corresponds to a recession speed of roughly 22,400 kilometers per second, about 50,000 miles per second, and the co-moving distance of around 1.1 billion light-years. You do not need the detailed math. The key idea is that this galaxy is not just big in size, it's sitting far out in the expanding universe, and we are seeing it as it was long before the Sun or Earth existed. Size and distance are only part of the story. Think about the number of stars. For the Milky Way, people usually quote something like a few 100 billion stars. That is already hard to imagine. Now, scale that up. Estimates for this galaxy put its star count around 100 trillion. That's about 1,000 times more than the low-end estimates for the Milky Way. If you tried to count one star per second, it would take you more than 3 million years just to count to 100 trillion. Even with that simple comparison, you can see that calling this galaxy large is an understatement. In terms of raw star numbers, it behaves less like a single galaxy and more like a whole small galaxy group that has been merged into one object. The environment around it makes the picture even more extreme. This galaxy is not sitting in isolation. It lies at the heart of a massive galaxy cluster called Abell 2029. A galaxy cluster is a huge structure where hundreds or thousands of galaxies, plus enormous amount of hot gas and dark matter, are all bound together by gravity. In that environment, this galaxy stands out so much that astronomers give it a special label. They call it the brightest cluster galaxy. That means it's the single most luminous galaxy in the cluster. Here is the striking part. By some estimates, this one galaxy alone is responsible for roughly a quarter of all the visible light from the entire Abell 2029 cluster. Imagine adding up the light from every other galaxy in that cluster and realizing that a single object in the middle is contributing something like 25% of the total. It's not just a central galaxy, it's a central galaxy that completely dominates its surroundings in brightness and mass. That dominance is a clue that it has spent billions of years growing by pulling in and merging with many other galaxies that fell toward the cluster center. All of this leads to the main point of this video. The system you are hearing about is not just a big galaxy that happens to be larger than usual. Its physical size, its extreme star count, its dominance inside its cluster, and especially the mass of the black hole that sits in its core all sit close to or beyond the upper edge of what our current models say galaxies should reach in the age of the universe. When astronomers simulate galaxy formation in a computer, they can make large ellipticals, they can grow impressive central galaxies and clusters, but objects like this push those simulations to their limits. So here is the tension that will run under everything from this point on. When someone says, "This is one of the biggest galaxies we have ever discovered," what exactly does that mean? How do you define the edge of something that fades so gradually into a faint halo that might stretch for millions of light years? How do you decide what counts as the galaxy and what counts as the surrounding cluster? And if this one object can reach these extremes, how many more like it are still hiding in the deep sky, waiting to force us to rewrite what we think a normal galaxy is? How can you call something the biggest galaxy if you can't even say clearly where it ends? That's the problem here, and it's not just a technical detail. It changes what that word biggest actually means. So let's break down how astronomers try to draw a line around an object that really doesn't want to have a clear edge. The first trick is something called D25. Do not worry about the symbol, think about the idea. A galaxy does not have a sharp border. The light just gets dimmer and dimmer as you move outward. So astronomers agree on a standard level of faintness, a standard surface brightness in blue light. And they say, where the galaxy's glow drops below this level, we will call that the edge. That level is what D25 is based on. For this galaxy, when you use that rule, you get an isophotal diameter somewhere around 124 to 170 kiloparsecs. In more normal terms, that is roughly 400,000 to 550,000 light years across, which is about 2.4 to 3.2 billion miles, around 3.8 to 5.2 billion kilometers. That is already several times the size of the Milky Way's visible disk, and that is just using one conservative way to define the boundary. So here is the first puzzle for you. If even the conservative edge of this galaxy is already that huge, what happens when you stop being conservative? The second way astronomers measure size is the effective radius. Again, the idea is simple. Instead of asking, where does the galaxy stop, they ask, how far out do you have to go to enclose half of all the light? That distance is the effective or half-light radius. For this galaxy, that radius is about 212,000 light years, which is around 1.2 billion miles, about 2 billion kilometers. And that number is only the distance to the half-light boundary. If you doubled it to get a rough full diameter, you are already well beyond the Milky Way's total size, and you still have not counted the very faint outskirts. So now you have two different sizes for the same object. One size based on a fixed surface brightness level giving you a diameter of a few 100,000 light years. One size based on half the total light, saying the inner region already beats our whole galaxy in extent. Which one is right for the label biggest? This is where the faint halo comes in and makes everything more extreme. When you take deep, careful images of this galaxy and you stack long exposures to bring out the dimmest light, you see that its glow doesn't really stop at the D25 line. There's a diffuse, ghostly halo of stars and intra-cluster light that you can trace out to about 600 kiloparsecs, which is close to 2 million light years from the center. At that distance, you're no longer just talking about the inner body of the galaxy, you're seeing stars that have been stripped from many galaxies and are now orbiting in the combined gravitational field of this galaxy and its cluster. So here is the next question you have to face. Do you count those stars as part of the galaxy or as part of the cluster around it? If you say, yes, they belong to the whole system built around this central galaxy, then suddenly this galaxy's effective diameter jumps from a few 100,000 light years to several million light years. It stops being an object that is just large and starts to look like a whole structure of galaxies that have been blended together over time. This is exactly why different research papers give very different numbers when they talk about how big this galaxy is. Some authors are strict. They only quote the bright inner body that stands clearly above the background sky. That gives diameters of 400,000, maybe up to 500,000 light years. Others say, no, the faint halo is physically connected. It is part of the same relaxed system, and they include more of the outer light. Then you start seeing numbers like 4 million light years across. And if you push all the way to the extreme outskirts, counting even more of the intracluster envelope, some estimates go up to 6 million light years. From the outside, that can sound like nobody knows what they're doing. But this disagreement is actually the result of looking more carefully, not less. The more we image this galaxy, the more faint light we find still connected to it, and the more the real size expands. So the drama is not fake. You can honestly say that for this galaxy, the more we look, the bigger it gets. So what should you, as a viewer, take away from all this? When you hear someone say, largest galaxy, you should not imagine a clean, bright disk with a neat border like a sticker on black paper. You should think, largest connected system of stars and diffuse intracluster light with one central galaxy at its heart. Under that kind of definition, this galaxy is, by several key measurements, a heavyweight champion. It has a bright main body that already outruns most galaxies we know. It has a half-light radius that beats the full sizes of big galaxies like the Milky Way. It has a halo and intracluster envelope that stretch out to around 2 million light years and beyond. But here's the real tension that this section sets up. If we have to argue this much just to define the size of one galaxy, how do we even find it in the first place, at a distance of 1 billion light years? And how did we realize that this faint blob in the sky was a monster at all? How do you even find something this extreme when it sits 1 billion light years away and in a small telescope barely shows up at all? The answer is that this giant did not start out as one of the largest galaxies we know. It started as a faint, anonymous smudge. In the late 1800s, when astronomers were building the Index Catalog, they logged an object now called IC 1101 as just another nebula, a fuzzy patch of light with no clear structure. At that time, nobody had proof that these nebulae were separate galaxies far beyond the Milky Way. This galaxy went into the catalog as one more faint blur, with no indication that it was anything special. So how did that little catalog entry turn into monster at the center of a massive cluster? The turning point was the idea that those nebulae might actually be whole other systems of stars. By the mid-20th century, astronomers were taking spectra of these faint objects, splitting their light into detailed rainbows and looking for the fingerprints of known elements. When they did that for this galaxy, the lines were all shifted toward the red end of the spectrum. That red shift was the first hard clue that this was not a small cloud nearby, but a huge galaxy very far away. Now the key question becomes, how far? When you measure the spectrum carefully, you get a redshift of about 0.077 to 0.078, and the recession speed of roughly 22,400 kilometers per second. Convert that and you get close to 50 million miles per hour, around 80 million kilometers per hour. That is not a one-time burst of motion. It is the result of the expansion of the universe, stretching the space between us and this galaxy. Plug that redshift into modern values of the Hubble constant, and you get a co-moving distance of about 354 megaparsecs, which is roughly 1.1 billion light years. In other words, every photon we detect from this galaxy has spent about 1 billion years crossing space to get here. You might wonder, if this galaxy is so massive and so luminous, why doesn't it dominate our sky? Why can't you just walk outside and point at it? The simple reason is that its huge physical size is crushed into a tiny patch of angle on the sky. Its apparent size is only about 1.2 by 0.6 arc minutes. For comparison, the full moon is about 30 arc minutes wide. So this galaxy spans an area on the sky that is dozens of times smaller than the moon, and its apparent brightness is around magnitude 14 to 15. Naked eye limit under ideal dark skies is around magnitude 6. That means this galaxy is thousands of times too faint for your unaided vision. So what do you actually see with real equipment? With a serious amateur telescope and a long exposure, it shows up as a small, elongated glow, brighter in the middle and fading smoothly outward. You would not look at that raw image and instantly think record-breaking giant. You would just log it as a distant elliptical. It does not scream for attention the way its physical properties suggest. Only when professional telescopes like Hubble and deep sky surveys like the Sloan Digital Sky Survey stack long integrations and analyze how the brightness changes with radius do you see how extended the profile really is and how much light is hiding down in the noise. Even that optical view is only part of the picture, because this galaxy sits at the heart of the Abell 2029 cluster, and that whole region glows in X-rays. Point an X-ray observatory like Chandra at this cluster, and you see a huge cloud of gas, tens of millions of degrees hot, filling the cluster and wrapping around the central galaxy. The X-ray emission peaks right on top of this galaxy, telling you that the deepest part of the cluster's gravitational well is centered there. Then you tune to radio wavelengths, and another key piece drops into place. Right at the core of this galaxy, observations pick up a bright radio source known as PKS 1508+05. High-resolution radio maps show jets and lobes extending out from the center, structures you only get when a supermassive black hole is feeding and launching streams of particles at near light speed. In Abell 2029, those radio jets sit inside the X-ray bright gas, interacting with it, bending and carving subtle structures. This combination, a powerful radio core and a central position in a hot X-ray atmosphere, is the classic signature of a very massive black hole sitting in the dominant galaxy of a massive, relaxed cluster. So now, step back and look at what you actually did to find this monster. First, someone a century ago wrote down a faint fuzz in a catalog. Decades later, people measured its redshift and realized it was over 1 billion light-years away. Then, deeper imaging showed that this faint glow was part of a dense knot of galaxies, a cluster. X-ray telescopes revealed a huge cloud of hot gas around it. Radio telescopes revealed a powerful central engine. At every stage, the object stayed visually unimpressive to the human eye, but the data kept pushing it higher and higher on every scale: distance, mass, luminosity, environment. And here's the part that really matters for you. Because its light has taken about 1 billion years to reach us, every observation of this galaxy is a look back in time to a universe that was roughly 12.8 billion years old. The sun didn't exist then. Earth didn't exist. The Milky Way was still evolving. Yet in that earlier universe, this galaxy had already reached the size and mass that challenge our ideas about how fast structures can grow. When you talk about this system, you're always talking about its past state, frozen into the light that is only now arriving. So the obvious next question is, if this thing was already that extreme 1 billion years ago, what kind of central engine did it need to get there? And what does that engine look like when you push black holes toward their upper limits? What happens when the engine in the middle of a galaxy is almost as extreme as the galaxy itself? That's the situation here. At the center of IC 1101, models based on the size of the depleted core point to an ultramassive black hole with a mass somewhere between about 4 and 10 times 10 billion suns, with a best estimate close to 10 times 10 billion. In plain language, that's roughly 40 to 100 billion times the mass of the sun, with a favored value around 98 billion. That puts the black hole in this galaxy right up against the theoretical limits for how big a black hole can get if it grows mainly by normal feeding, pulling in gas at or below the usual radiation limit. So what does a number like that actually mean? A black hole's size is usually described by the radius of its event horizon, the point of no return. That radius grows in direct proportion to the mass. Double the mass, double the radius. The black hole at the center of this galaxy would have an event horizon so large that light would take days to circle it. For a rough sense of scale, if you swapped the Sun for a one solar mass black hole, the event horizon would be just a few miles, a few kilometers across. Scale that up to tens of billions of solar masses, and the event horizon swells to a region larger than the orbit of Earth, pushing out into a zone comparable to the orbits of the outer planets, with light taking many hours to days to go around once. Now, compare that to what you have at home. In the Milky Way, the central black hole, Sagittarius A, is about 4 million times the mass of the Sun. That is big, but in the supermassive black hole family, it is actually on the small side. The object in this galaxy is about 10,000 to 25,000 times more massive than Sagittarius A. The event horizon of our black hole would fit inside the event horizon of this one thousands of times over. If you could somehow place this ultramassive black hole where Sagittarius A sits now, it would dominate the inner region of our galaxy in a way that is hard to overstate. And the part of space where its gravity is the main player would extend over light-day scales, not light-minute scales. But mass alone is not the full story. The real impact comes from what that much mass does when it is actively feeding. Observations in radio wavelengths show that the central region of this galaxy hosts a powerful radio source called PKS 1508 plus 059. High-resolution radio maps reveal jets and broad, bent radio tails extending out from the core. Those structures are classic signs of an active galactic nucleus, a black hole that, at least at times, has been gulping down gas and launching twin streams of particles at close to light speed. Now, put that together with the X-ray view. Chandra and other X-ray missions show that the core of the Abell 2029 cluster around this galaxy is filled with gas heated to tens of millions of degrees. That hot gas shines in X-rays and sits in a kind of rough equilibrium in the cluster's gravitational well. You would normally expect such gas to cool over time, lose energy, and start flowing inward, feeding star formation in the central galaxy. But in this cluster, you do not see the strong cooling flow you would predict from simple models. Instead, the energy from the black hole's jets and outflows appears to be reheating the gas, stirring it, and keeping it too hot and too pressurized to collapse efficiently. So, you get a feedback loop. Gas falls toward the center, the black hole feeds, it turns on as an active nucleus, it launches jets and blows bubbles or disturbances into the hot atmosphere. That input of energy heats and stirs the gas, and that slows down further fuel supply. This back and forth acts like a crude thermostat for the whole cluster core. Turn the accretion up too high, and the jets blast more energy into the gas, making it harder for new gas to reach the center. Turn it down, and cooling can slowly restart. In this galaxy, the black hole is powerful enough that its feedback is not just shaping a small region near the core, it is influencing gas over hundreds of thousands of light years. Here is the next issue. In most galaxies, the mass of the central black hole follows fairly tight relationships with the surrounding galaxy. There's a correlation between black hole mass and the stellar mass of the central bulge, and another between black hole mass and the speed at which stars move in that bulge, the so-called velocity dispersion. For normal galaxies, if you know one, you can roughly predict the other. But brightest cluster galaxies tend to break these rules. Studies show that for a given bulge mass or velocity dispersion, their black holes are often overmassive, much heavier than those standard relations would suggest. This galaxy looks like part of that pattern, with a black hole that is far above what you'd expect if you just apply the usual Milky Way calibrated formulas. Why does that matter? Because those scaling laws are one of the main tools we use to estimate black hole masses across cosmic history. If they stop working at the high mass end, then a lot of our quick estimates for the biggest systems may be wrong. Brightest cluster galaxies like this one seem to follow a different rule. Their black hole masses correlate better with the size of their depleted cores than with the usual bulge properties. That suggests a growth history dominated by repeated mergers of both galaxies and black holes, carving out huge cores and building unusually massive central objects. And underneath all of this, there's a deeper tension. Theoretical work points to an approximate upper limit for black hole masses, set by the balance between how fast a black hole can pull in gas and how much radiation pressure that infalling gas produces. For typical black hole properties, that limit is on the order of a few times 10 billion solar masses, maybe up to around a few hundred billion in extreme cases. When you start measuring or inferring black holes in the range of 50, 60, 100 billion solar masses, as in some of the most extreme galaxies and clusters, you are operating very close to those limits. If the central black hole in this galaxy really is near the high end of those estimates, then it's one of the sharpest tests we have of black hole growth models. To reach such a mass in 13.8 billion years, you probably need not just steady Eddington-limited feeding, but also periods of more rapid growth and multiple mergers of already large black holes. At the same time, the feedback from such a monster has to be strong enough to shut down star formation in the central galaxy and keep most of the surrounding gas hot and dilute. That combination of extreme growth and extreme self-regulation is not something our simplest models handle well. So, the stakes are clear. Objects like this are not just curiosities. If these ultramassive black holes really are as big as the data suggest, they're telling us our standard picture of how fast black holes can grow and how they co-evolve with their host galaxies and clusters is missing something important. And if the central engine can bend the rules this much, you should ask one more question. What has all of this done to the visible structure of the galaxy itself, especially in the region closest to the black hole? How big does a galaxy's empty center have to be before that center is bigger than most galaxies you've ever heard of? That's exactly what you're dealing with here. High-resolution Hubble data show that IC 1101 has what astronomers call a depleted core with a break radius of about 4.2 kiloparsecs, which is roughly 13,700 light-years across, about 80 quadrillion miles, or around 130 quadrillion kilometers. That number is not a guess. It comes from fitting the brightness profile and finding where the inner, flattened region transitions to the outer, steeper light distribution. Typical big ellipticals have core sizes in the range of 20 to 500 parsecs. This galaxy's core is about 10 times larger than the cores of other giant ellipticals like NGC 4889 and NGC 1600, making it the largest galactic core measured so far. So what does core actually mean here, and why do people call it depleted? If you plot how bright this galaxy is as you go outward from the center, you don't get a simple curve. For most of the galaxy, the light follows a smooth mathematical pattern called a Circic profile, which describes how many stars you have at each radius. But right near the center, that smooth rise suddenly flattens out. The inner region is dimmer than the outer curve says it should be. To model that properly, astronomers use a core Circic profile. Outside, the usual Circic law. Inside, a shallower, scooped-out section. That inner flat part is the depleted core. It is not empty, but compared to what you would expect if you extended the outer profile inward, there are a lot fewer stars than should be there. Once you have that model, you can ask a brutal question. How much stellar mass is missing from that central region? For this galaxy, the answer is extreme. The best fits give a stellar mass deficit of about 4.900 billion times the mass of the Sun. In other words, if you recreated the undisturbed brightness profile and then subtracted what's actually there now, you've effectively removed a few hundred billion solar masses worth of stars. That missing mass is on the order of the total stellar mass of a large galaxy by itself. It also corresponds to roughly a quarter to a third of the original spheroid's light, carved out of the middle. To make that more concrete for you, think of it this way, very literally. You start with a huge, dense central bulge of stars. Then something happens that ejects, reallocates, or shuffles away the equivalent of an entire Milky Way-sized galaxy's worth of stars from the center to larger radii, or even right out of the galaxy. What's left behind is a core that looks oversized and underpopulated compared with galaxies that have grown more gently. When astronomers say this galaxy has a depleted core, they're not talking about a subtle tweak. They're talking about a central region where the deficit alone is comparable to a whole massive galaxy. So, what could possibly do that to stars locked in a deep potential well? The leading explanation is that the core has been scoured out by multiple mergers of supermassive black holes. Every time this galaxy merged with another giant, each one brought in its own central black hole. Over time, those black holes sank toward the new common center through dynamical friction, formed a tight binary, and then started interacting with nearby stars. In a three-body interaction, a star can pass close to the black hole pair and get flung out at high speed, while the binary loses orbital energy and tightens. Repeat that process over and over, and you literally evacuate stars from the center, kicking them into the outer halo, or even unbinding some of them from the galaxy entirely. The numbers in this galaxy say that this did not happen just once or twice. If you naively apply standard relations between core mass deficit and black hole mass, you'd infer dozens of so-called dry major mergers, more than is realistic for a single object. That mismatch is part of the reason astronomers think the central black hole here is overmassive relative to standard scaling laws. It also hints that something even more dramatic may have occurred, like a gravitational wave recoil, where the merged black hole gets a kick and oscillates through the core, doing extra damage on each pass and throwing out still more stars. The result is a core that is too large and too empty to explain with normal small number merger histories. You can see independent evidence of that violent history in the shape of the galaxy's outer light. When you map the regions of equal surface brightness, the isophotes, you find that the main body and the core line up neatly, but the faint halo is twisted by about 20 degrees relative to them. On top of that, those isophotes are not perfect smooth ellipses. They are boxy, slightly squarer in shape. Both effects are classic signs of a system that has been through multiple major mergers, with streams of stars and dark matter coming in from different directions and being mixed into a single huge envelope. There are also hints of an inner, more elongated feature that might be a nuclear disk or the remains of a disrupted satellite near the sun, again pointing to past interactions. Put all of this together and you get a clear message. You are looking at a piece of forensic evidence for how this galaxy grew. The enormous depleted core tells you that ultramassive black holes at the center have done serious gravitational work on their surroundings. The twisted, boxy halo tells you that the outer parts have been built by repeated mergers and tidal stripping events in the cluster. Cores this large are incredibly rare. Only a handful of galaxies come close, and this one is at the top of the list. That makes it a key test case. If your models of galaxy and black hole evolution cannot produce a system with this kind of core size, mass deficit, and structure, then your models are missing something big about how brightest cluster galaxies assemble. And that raises the next question you should be asking. If the center has been carved out this violently, and if the mergers and black hole activity have been going on for billions of years, what does that do to the stars that remain? What kind of stellar population is left inside a galaxy that has already gone through this many collisions and this much feedback? Are its stars young and forming, or is the whole system basically in retirement, just fading out? Why would one of the biggest galaxies you've ever heard about glow soft golden light instead of bright blue like a huge star factory? That color is your first hint that this thing is old, tired, and basically running on leftover fuel. IC 1101 is a supergiant elliptical at the center of the Abell 2029 cluster, and when you look at its combined light, it's dominated by yellow, metal-rich stars. There's very little of the hard, bright blue light you get from short-lived, massive young stars. In practice, that means the stars in this galaxy are mostly older, lower-mass populations that have been shining for billions of years, not brand-new stars burning through gas at a crazy rate. So what does that actually tell you in simple terms? Blue light means rapid, recent star formation. Young, massive stars burn hot and blue, but they die fast in tens of millions of years. If a galaxy is actively forming a lot of new stars, those big blue giants dominate the color. If instead you see a smooth golden or reddish glow, that's a sign that those big blue stars are mostly gone and you're looking at older, longer-lived stars, a mix of solar-type stars and cooler red giants and dwarfs, many of them enriched with heavier elements from past generations of supernovae. This galaxy falls into that second category. It's red and dead in the astronomer's shorthand. Red because older stars dominate the light, dead because little new star formation is happening now. That color leads straight into the next question. How old are the stars you're actually seeing here? When people model the stellar populations in this galaxy, they find a lot of evidence for very old stars, with many of them several billion years older than the Sun. Some estimates suggest populations up to around 7 billion years older than our star, which means a big chunk of this galaxy's mass was already in place and shining long before the solar system even formed 4.5 billion years ago. In other words, while Earth was still just a future possibility in a collapsing cloud of gas, this galaxy was already massive and mature. And remember the scale here. You're not talking about a few old star clusters, you're talking about a system with on the order of 100 trillion stars. That's 1,000 times more than the lower estimates for the Milky Way. If a large fraction of those are older than the Sun, then this galaxy has been building, merging, and aging through most of cosmic history. It didn't just quietly assemble in the background, it grew fast and early, then settled into a long, slow fade. The age of its stars backs up the idea you saw in the core section. This galaxy did a lot of its serious growth early through major mergers in the dense center of its cluster, and now it's just coasting. Once you accept that the stars are old, the obvious next question is any meaningful star formation still going on, or is this thing basically in retirement? Observations say it's basically retired. Brightest cluster galaxies like this one are typically almost empty of cold gas, which is the raw material you need to make new stars. Instead, they're surrounded by hot, X-ray emitting gas at tens of millions of degrees sitting in the cluster potential. Cooling of that gas is heavily suppressed by feedback from the central black hole. For most central cluster galaxies in systems like Abell 2029, the current star formation rates are tiny compared to their total mass, often around 1/10 of a solar mass per year or less. For something with the mass and size of this galaxy, that's effectively zero in relative terms. Put that in perspective. A galaxy with 100 trillion stars and a star formation rate of well under 1 solar mass per year is basically not changing its total stellar mass anymore. It's not building major new structures, not forming big batches of bright blue stars that would change its color. The big story now is the aging of the stars it already has. That's why the integrated light looks golden. You're seeing the glow of an old population that has had its gas supply cut off or heated so much that it can't cool back down to make new stars efficiently. But if you have that many stars, the next natural question is, what does that mean for planets? Here, we have to be careful because at 1 billion light-years, we can't detect individual planet systems in this galaxy. We can't see exoplanets there the way we do in the Milky Way. What we can do is apply what we've learned about planets around nearby stars. In our own galaxy, when you add up all the detections and the statistics from missions like Kepler, you get a rough average of at least 1 planet per star, and probably more like 1 to 2 planets per star, counting everything from small rocky worlds to giant gas planets. If you apply that very conservative 1 to 2 planets per star rule to this galaxy's estimated 100 trillion stars, you get on the order of 100 to 200 trillion planets. That's a rough order of magnitude extrapolation, not a precise count, but it gives you the right sense of scale. You're looking at a system that could host 1,000 times more planets than the Milky Way. Most of those worlds will never be individually known to us. They're too far away. Their host stars blend into the smooth light profile, and current exoplanet techniques just can't reach that distance. But statistically, if planet formation here works anything like it does in our part of the universe, this galaxy should be packed with planets. That raises a tougher, more unsettling question. In a place dominated by old stars and weak star formation, what kind of environments do those planets live in? In the dense central regions, orbits can be chaotic over very long times, and the radiation environment may have been intense when the central black hole was more active. In the outer halo, stars can drift through a much quieter, darker environment, with fewer close neighbors and a dimmer background. Whatever the mix is, the key point is that this galaxy has had billions of extra years for any potential life to arise and evolve compared to Earth. If life ever did emerge on some of those planets, it would have had a major head start on us. But from here, that is just speculation. All we see is the integrated light of old stars and the indirect clues from their colors and spectra. So with that many stars, almost no fresh gas, and a color that screams aged population, what is the long-term fate of this galaxy? The answer is simple and a bit bleak. With star formation mostly shut down, the existing stars will keep aging. The most massive ones are already gone. Over the next billions of years, more stars will exhaust their fuel, swell into red giants, shed their outer layers, and leave behind white dwarfs, neutron stars, and black holes. The overall brightness will slowly decline as the bright intermediate mass stars die off and the light becomes dominated by long-lived faint red dwarfs and stellar remnants. At the same time, the central black hole and the cluster environment will keep the surrounding gas hot and spread out, preventing any major new bursts of star formation. Without fresh fuel, this galaxy's future is one of gradual dimming. Over very long timescales, it will go from a hyper-luminous, brightest cluster galaxy to a more subdued, diffuse glow. And on the largest scales of cosmic time, as dark energy drives galaxies farther apart and stars everywhere burn out, even a system this huge is headed for the same endpoint as everything else, a giant fading ember against an infinitely empty background. And that brings you to the next step in the story. If this galaxy is already old, gas-poor, and fading, how did it get so massive in the first place? What did it have to do to the rest of its cluster to end up with 100 trillion stars and a multi-million light-year halo? And how many other galaxies had to be torn apart to build it? How do you get a galaxy this big in the first place? The short answer is, you don't build it from scratch, you feed it other galaxies until almost everything nearby is gone. IC 101 sits in the middle of a structure called Abell 2029, and to understand what this galaxy really is, you have to see it as the central object in a whole city of galaxies, not just a single island in space. Abell 2029 is a rich galaxy cluster, roughly 1.0 to 1.1 billion light-years away. It spans about 5.8 to 8 million light-years across, which is on the order of 3 to almost 5 times 10 quintillion miles, around 6 to 8 times 10 quintillion kilometers. Inside that volume, there are thousands of galaxies, from big ellipticals down to tiny dwarfs, all orbiting in one massive dark matter halo and embedded in a cloud of hot, X-ray emitting gas. This galaxy sits right at the geometric and dynamical center of that structure, the brightest cluster galaxy, exactly where you'd expect the main anchor of the cluster to live. So here's the next question. If a cluster has thousands of galaxies, why is there only one that's this dominant in the core? In many rich clusters, you find several very bright galaxies sharing the inner regions, something like multiple major cities in the same metro area. Abell 2029 doesn't look like that. Observations of its galaxy luminosity function show that the central region is almost empty of other very bright galaxies. There is this galaxy, and then a big gap, and only then the rest of the population. That pattern is a red flag that many former giants near the center were swallowed over time, leaving one hyper-dominant central galaxy plus a surrounding cloud of much smaller companions. If those big neighbors are gone, where did their stars go? This is where the faint, extended light around this galaxy becomes crucial. Deep optical imaging of Abell 2029 shows a huge, smooth, low-surface brightness halo around the central galaxy, stretching out to hundreds of thousands of light-years, and when you push down into the noise, to about 600 kiloparsecs, or roughly 2 million light-years from the center. This very faint glow is called intracluster light. It is made of stars that are no longer tightly bound to any single galaxy. Instead, they orbit in the overall potential of the cluster, Around this galaxy, that intra-cluster light blends almost seamlessly into its own diffuse envelope. The best explanation for that smooth, extended halo is repeated tidal stripping and mergers. As smaller galaxies fall toward the cluster center, gravity pulls on them unevenly. Stars in their outer parts feel a stronger tug from the cluster and the central galaxy than from their original host. Over time, those galaxies are stretched, distorted, and gradually shredded. Some stars are captured into the outer halo of this galaxy, adding to its size and mass. Others are kicked into orbits that take them all around the cluster, becoming part of the intra-cluster light. On top of that, major mergers of big galaxies near the core dumped entire stellar systems into the central object. After billions of years of this process, you end up with exactly what you see here. One swollen central galaxy wrapped in a vast, smooth glow of unbound or loosely bound stars. You can also see the cannibal story in the motions of the galaxies themselves. Spectroscopic surveys of Abell 2029 have measured redshifts for more than 1,000 cluster members and built up a velocity distribution. The galaxies in the cluster show a large velocity dispersion, roughly around 1,400 to 1,500 kilometers per second, which tells you the gravitational well is extremely deep and massive. In that distribution, this galaxy sits near the dynamical center with only a small motion relative to the cluster mean. It behaves like the bottom of the potential well, the point everything else orbits around. On smaller scales, measurements of the stellar velocity dispersion inside this galaxy show something important. As you go farther out into its halo, the random speeds of the stars rise, approaching the same kind of values you see for galaxies orbiting in the cluster. That tells you the outer parts of this galaxy are not just a normal galactic halo. They're already feeling and tracing the cluster's overall gravity. The transition from stars bound mainly to the galaxy to stars moving in the cluster potential is smooth, which fits perfectly with the picture that the envelope and intracluster light were built by stripping and merging over a long time. Put those pieces together and the growth history becomes clear. Early on, the cluster began as many smaller groups collapsing together. The proto-central galaxy sat near the deepest part of the dark matter halo and started accreting material. Other big galaxies fell in, merged, and lost their distinct identities. Smaller members were repeatedly harassed and stripped on their orbits. Each event fed more stars, more gas, and eventually more black holes into the center. Over billions of years, that process produced this galaxy, a supergiant central system that has effectively eaten many of its peers, dominating the light and stellar mass budget in the core. For you, the stakes are simple and high. When you think about this galaxy now, you shouldn't picture a single object that just happened to form large. You should see the end product of cluster-scale violence, dozens of major galaxies shredded, their stars folded into one central monster and its halo, their black holes dragged inward to help carve out the enormous depleted core you heard about earlier. The size, the mass, the intracluster light, and the lack of rival giants nearby are all different angles on the same story: extreme cannibal growth in the densest parts of a massive cluster. And that raises the next, more unsettling question. If the visible stars and stripped halos only tell part of the story, what does the hidden mass look like, the dark matter halo that actually holds this whole system together and stretches out to those 2 million light-years and beyond? How do you know this galaxy is truly monstrous, not just in light, but in actual mass, when most of that mass is invisible? The answer is, you watch how everything else moves around it, and you compare how much light you see. When astronomers model the motions of stars in this galaxy and the orbits of other galaxies in the cluster, they find that as you go out to around 200 kiloparsecs for the center, that's roughly 650,000 light-years, or about 4 quadrillion miles, around 6 to 8 quadrillion kilometers, inside that volume, the mass-to-light ratio shoots above 100 solar masses for every unit of solar-type light. In simple terms, for every sun's worth of visible glow, there are at least 100 suns worth of mass. Stars alone cannot explain that. Gas cannot explain that. The only way to make the numbers work is to say that most of the mass in this region is dark matter, matter that has gravity but does not emit light we can see. If that sounds abstract, think about it this way. You can calculate how much mass you'd need to keep stars and galaxies orbiting at the speeds you observe. That gives you a required mass. Then you add up how much mass you think is in the stars based on the light. If the required mass is 10 times larger than the visible mass, you already know there's a dark component. In this galaxy and its immediate surroundings, once you get a few 100,000 light years out, that mismatch is not just 10 times, it is 100 times or more. That is why astronomers say the outer regions are dark matter dominated. The luminous galaxy is sitting in the middle of a much larger, much heavier, invisible halo. So how far does that halo go? Observationally, we can trace the combined effect of stars plus dark matter using the very faint halo and intracluster light. Deep imaging of this galaxy in Abell 2029 shows that its diffuse envelope is detectable out to about 600 kiloparsecs, which is close to 2 million light-years from the center, or about 12 quintillion miles, around 20 quintillion kilometers. Beyond that, the signal sinks deeper into the general intracluster light. But by then, you have already crossed the distance scale that dwarfs most galaxy groups we're familiar with. If the visible stars and strip material reach that far, the underlying dark matter halo is at least that big, and in practice probably stretches even farther before it blends into the overall cluster halo. You might ask, isn't that just guessing from light again? No, because astronomers have another way to weigh the system that does not care what kind of matter is doing the pulling: gravitational lensing. Light from even more distant background galaxies passes through the space around Abell 2029 on its way to us. As it moves through the cluster's gravitational field, its path is slightly bent. When you look at many background galaxies behind the cluster, their shapes are statistically distorted in a preferred pattern. This is called weak gravitational lensing. By measuring those tiny distortions, you can reconstruct a map of where the mass is, regardless of whether it's in stars, gas, or dark matter. Weak lensing studies of Abell 2029 show a strong concentration of mass centered on this galaxy and the cluster core. The lensing signal extends to scales of a couple of megaparsecs, several million light-years, and the total mass implied is enormous, much more than you can get from the stars and hot gas alone. The lensing map and the light map do not match one-to-one. The light is clumpy, located in galaxies. The mass, dominated by dark matter, is more smoothly spread, but peaks sharply at the center where this galaxy lives. That independent weighing agrees with the dynamical modeling. Most of the mass here is dark. On top of lensing, you have the X-ray emitting gas as another mass tracer. The cluster core, including the space around this galaxy, is full of gas heated to tens of millions of degrees, glowing in X-rays. That gas sits in what's called hydrostatic equilibrium. Its pressure balances the pull of gravity from the cluster's total mass. If you know the temperature and how its density changes with radius, you can solve the hydrostatic equations and infer how much mass you need at each distance to keep the gas from collapsing or flying apart. When astronomers do that for Abell 2029, they again find that the total mass rises steeply with radius, and that dark matter outweighs normal matter by a large factor, on the order of 5-to-1 or more. So now you have three independent lines of evidence all saying the same thing. First, the motions of stars and galaxies, which tell you need far more mass than the stars can provide. Second, the weak lensing distortions of background galaxies, which map a massive, extended, unseen halo centered on this galaxy. Third, the distribution of hot X-ray gas, which traces a deep potential well that only a huge amount of dark matter can generate. Each of these methods has its own assumptions and sources of error, but they converge on one consistent picture. This galaxy is embedded in a dark matter halo that stretches for millions of light years and contains most of the cluster core's mass. What does that mean for how you think about the galaxy itself? It means the bright stars you see in images are just a thin skin, the glowing frosting on top of an invisible bulk. The shape of the orbits, the speeds of the stars, the scale of the intra-cluster light, all of that is set by the dark halo. If you could somehow turn off the stars, the cluster's gravity field would hardly change. But if you could turn off the dark matter, the entire structure would fly apart. The stars in this galaxy and the rest of Abell 2029 would not have enough mass on their own to hold everything together at the observed velocities. This has a direct impact on the whole biggest galaxy idea. When you say that this galaxy has a halo extending to 2 million light-years, you're really describing the region where its influence, plus the clustered dark matter peak, dominate the motions of stars in stripped material. You're no longer talking about just a visible object. You're talking about a dark matter structure that happens to host a huge central galaxy and a massive black hole at its center. The luminous part is what we can easily photograph, but in terms of gravity, of structure formation, and of long-term fate, the dark component is the main actor. So the big picture is this. This galaxy's visible light is only a tracer. The true size and power of the system are set by a dark halo that reaches across millions of light-years and outweighs the stars by an order of magnitude or more. When you think of it as the biggest galaxy, you should mentally add sitting inside one of the most extreme dark matter wells we can directly study. And that sets up the next problem. If the visible part is already weird and the dark halo is this huge, where does this system sit compared to more normal galaxies like the Milky Way, or even giants like M87? Are we still in the same category at all, or does this object force us to rethink what a galaxy even is? At what point does a galaxy stop feeling like a bigger Milky Way and start feeling like something else entirely? Let's put some hard numbers next to each other and see where that line breaks for you. Start with home. The Milky Way's visible disk is roughly 150,000 to 200,000 light-years across, depending on how far into the faint outskirts you count. That already sounds huge, but it's still a fairly normal, large spiral galaxy. Now look at M87, the giant elliptical in the Virgo cluster. Its stellar body stands about 240,000 light-years, so a bit bigger than the Milky Way, and it already looks massive and dominant in its environment. Then you stack those against this galaxy. When you include its extended halo and intra-cluster envelope, you're not talking a few 100,000 light-years anymore. You're talking about a structure whose halo reaches something like 4 million light-years or more in diameter, with faint light and stripped stars traceable out to about 2 million light-years from the center. The jump from a couple 100,000 to millions is not a small upgrade. It's a change of category. Now add star counts. The Milky Way and Andromeda each host a few 100 billion stars, say 200 to 400 billion as a ballpark. Big numbers, but still in the hundreds of billions range. Estimates for this galaxy's stellar content cluster around 100 trillion stars. That's about 1,000 times more than the low-end numbers for the Milky Way. If you lined up galaxies by star count, the Milky Way and Andromeda would sit in the mid to high range for normal spirals. This one would be way down the table, in a column where your labels stop saying large galaxy and start saying this is what you get when you mash a whole small group of galaxies together and keep feeding it. So here's the obvious question. If the sizes and star numbers are that far off the usual scale, do the standard rules for galaxies still apply? Astronomers use a bunch of empirical relations to describe normal galaxies. There's a relationship between how bright a galaxy is and how big it is. There's one between the total mass of stars and the random speeds of those stars, the velocity dispersion. There are correlations between black hole mass and bulge mass, between surface brightness and radius, and so on. For ordinary ellipticals, these relations form fairly tight sequences. You can take one property, plug it into the formula, and get a decent guess for another. Brightest cluster galaxies, especially systems like this one, do not sit nicely on those traditional lines. On size versus luminosity plots, they're too big for how bright they are, or too bright for their central surface brightness. On the black hole versus bulge mass relation, they sit high. Their black holes are overmassive for the amount of starlight in the bulge. On the fundamental plane relations that connect size, brightness, and kinematics, they behave like outliers. That tells you that the way they grew is not just a scaled-up version of how a normal elliptical grows. The physics is different because the environment is different. Instead of living in relative isolation, they're sitting at the bottom of a deep cluster potential fed by repeated mergers and tidal stripping on cluster scales. You might wonder then, is this actually the largest galaxy, or is it just the one everyone talks about? The honest answer is messy. Other brightest cluster galaxies like the central giants in Abell 1413 or ESO 306-17 also have enormous halos and intra-cluster light. Depending on exactly how you draw the boundary, whether you count only the bright body or include more of the faint envelope, some of them can reach similar or even larger diameters. Radio galaxies like Alcyonies can span about 16 million light-years in their radial lobes, if you count jet structures as part of the galactic extent. So in a strict one-number ranking, there is room to argue. But this galaxy still matters in a special way. It has a few things those other contenders don't combine as cleanly. It has one of the largest measured depleted cores. It has a stellar mass and star count in the 100 trillion range. It has an extremely extended halo and intra-cluster envelope that can be mapped in detail. It sits in a well-studied cluster with good X-ray, optical, and radio data. It likely hosts an ultramassive black hole near the upper end of what standard theory allows. That combination makes it an ideal poster child for the phrase, "too big to be comfortable." When someone wants to show you what happens when the universe pushes galaxy growth to the limit, this is the example they reach for. There's another angle here that's important for you to see. Once you put galaxies like this next to everyday systems, the idea of a single normal galaxy stops making sense. On one end, you have tiny dwarf galaxies with a few million stars, sometimes less, barely holding themselves together. In the middle, you have spirals like the Milky Way, big and complex with ongoing star formation and structured disks. Above that, you get regular giant ellipticals and central galaxies in modest groups. And then beyond even those, you have systems like this one, sitting in massive clusters with halos spanning millions of light years, star counts in the trillions, and black holes in the tens of billions of solar masses. Calling them all galaxies with the same mental picture is like using the same word for a small village and a continent-spanning megacity. Technically correct, but misleading. For you as a viewer, the stakes are about how you picture the universe. If you only think in terms of Milky Way-type galaxies, you're missing the extreme tail of what structure formation can do. The universe doesn't just make lots of similar disks and ellipticals. It also makes miniature clusters where a dark matter halo, several million light-years across, has collapsed, merged, and funneled material into one central boss galaxy. That boss has eaten many of its neighbors, carved out an oversized core, and now sits at the bottom of a deep potential surrounded by a diffuse envelope of orphan stars. And that leads directly to a more personal question. If the universe can build a system that huge, with that many stars and that much time to evolve, what would it actually feel like to live inside something like this, instead of in a modest spiral like the Milky Way? How different would your sky, your neighborhood, and even the dynamics of your local group be if this galaxy took the Milky Way's place? What would actually change for you if overnight the Milky Way got swapped out for IC 1101 and everything else in our neighborhood had to deal with that upgrade? Let's walk through that step by step because the numbers here quietly destroy the picture you have of where we live. Start with the local group, the little family of galaxies you're in right now. It includes the Milky Way, Andromeda about 2.5 million light-years away, the Triangulum galaxy, and a few dozen dwarf galaxies. Altogether, this local group fits inside a sphere roughly 10 million light-years across. That sounds huge, but compare it to the core plus halo of this galaxy. The extended halo we've been talking about reaches around 4 million light-years across, maybe more depending on how you define the edge. If you dropped this galaxy right where the Milky Way is, its hot core and stellar envelope would easily cover the entire space currently between us and Andromeda and push far beyond. The Milky Way and Andromeda would not be two separate approaching giants anymore. They would have been swallowed long ago and turned into parts of one central system. So here's the first big shift to keep in mind. The local group stops being a group. It becomes the inner region of a central galaxy inside a much larger cluster environment. The separate identities of the Milky Way, Andromeda, and most of the dwarfs vanish. Their stars are now either in the thick central body of this galaxy or out in its extended halo or mixed into the intra-cluster light. What you think of as our galaxy turns into just one past meal, one event in a long history of cannibalism. Now, what would the sky look like if the sun sat inside that environment instead of the Milky Way's disk? Imagine the sun not 30,000 light years from the center like it is now, but maybe 50,000 light years out from the core of this galaxy, somewhere in the inner halo. You would still have a night sky full of stars, but the pattern would change. Instead of a thin Milky Way band across the sky, you would see a much thicker, brighter central bulge dominating one part of the sky, packed with old yellow stars. The density of background stars would be higher in many directions because you're inside a bigger, more extended stellar system. You would also see more elliptical satellites rather than pretty spiral companions. Many of the surviving satellites in a system like this are small, gas-poor, battered galaxies, not clean spirals with blue arms. In deep images from a dark site, the sky would show a swarm of faint, smooth blobs, the remnants of smaller galaxies living under intense tidal stress. The overall impression would be a sky defined by a huge central glow and a halo of old light, not a neat spiral disk. That brings up the next point, the tidal environment. In a cluster core with a galaxy this massive at the center, the gravitational field changes more quickly with distance than it does in the local group. Smaller galaxies and even thick stellar streams feel stronger differences in gravity between their near and far sides. That tidal pull stretches and squeezes them. Over time, it strips gas and stars from their outer regions, making them puffier and more diffuse. Right now, in the local group, dwarf galaxies around the Milky Way and Andromeda are being stripped and stirred, but the process is relatively slow, and a lot of them still retain gas and some star formation. In the environment of this galaxy, the same kind of satellites would be under much harder harassment. Their gas would get removed faster by both gravity and the hot intra-cluster medium. Their stars would be peeled off and added to the central galaxy's halo. The whole cannibalism story that you heard about earlier would be happening closer to home, on shorter timescales, and with more victims. So what does that do to your immediate neighborhood, to the orbits that actually matter for life on Earth? Interestingly, at the scale of individual solar systems, not much changes. Gravity is local. The main force shaping Earth's orbit is still the sun, not the galaxy. Even if you put the sun inside a much massive galaxy, the extra pull on a planet at one astronomical unit is tiny compared to the sun's own gravity. So the basic orbital period, the seasons, and the structure of the solar system stay almost the same. But the orbits on galaxy scales would be completely different. In our real universe, the Milky Way and Andromeda are on a slow collision course that will play out over billions of years. The local group is loosely bound, with galaxies still settling into a long-term configuration. If you replace the Milky Way with this galaxy, that whole story disappears. Andromeda and its satellites would have merged into the central system long ago. There is no approaching collision in the future. The collision already happened and is part of the reason the central galaxy is so big. The orbital paths of surviving dwarfs and streams would be shaped by the dark matter halo and the cluster potential, not by a simple Milky Way-Andromeda pair. On even larger scales, the space that used to be a quiet region between two big galaxies becomes the bright, dense core of a cluster. Instead of seeing Andromeda as a single bright object in the sky, you would see many smaller remnants, long tidal tails, and a thicker background of unresolved stars. The large and small Magellanic clouds in this scenario could have ended up as faint, stretched-out plumes in the halo, or been completely torn apart and mixed into the diffuse light. So what's the psychological punch in all this? What does it do to the way you think about our galaxy? In a local group dominated by a system like this, the Milky Way would not stand out as a main character. It would be one of the many building blocks that went into the center, one ingredient in a long recipe of mergers. Its stars would now be scattered across the central bulge and halo of a larger object. Its central black hole would have merged into a much more massive one. The history of the Milky Way, with all its spiral structure and satellite system, would be something you could only reconstruct statistically from the mix of stars in the core, not something you could point to in the sky. From that point of view, the Milky Way stops feeling like a huge, permanent home galaxy and starts feeling like a minor phase in the life of a bigger system. It becomes a footnote. The identity shift is the key thing here. In your current mental picture, the Milky Way is the galaxy, and the local group is its neighborhood. In a universe where this galaxy took its place, the local group is gone, the Milky Way is digested, and the main character is a central monster wrapped in a multi-million light-year halo inside a massive cluster. And once you see that, another question opens up immediately. If a galaxy like this can absorb whole systems the size of the Milky Way and Andromeda, and if it holds something like 100 trillion stars, how many worlds does that actually translate to? And what kind of environments from the violent core to the lonely outer halo would those worlds experience over billions of years? How many possible worlds are you talking about when you say this galaxy has around 100 trillion stars? Let's put a rough number on it, even if it's an estimate, because that's the only way your brain can start to feel how big this is. In our own galaxy, exoplanet surveys tell you that planets are common. On average, you're looking at roughly one planet per star, and probably more if you include small, cold worlds that are hard to detect. So if this galaxy really has something like 100 trillion stars, then even a very conservative assumption of one planet per star gives you around 100 trillion planets. Push that average to 2 planets per star, and you're up at 200 trillion. Either way, you're dealing with a system that could hold roughly 1,000 times more planets than the Milky Way. This is not a precise census, it's an order of magnitude extrapolation, but it's based on the same statistics we use to say that planets are everywhere in our neighborhood. Now, raw planet count is one thing. The next question is, what kind of stars are those planets orbiting, and does that help or hurt the chances for interesting chemistry and maybe even life? A key factor is metallicity, which in astronomy just means how many elements heavier than hydrogen and helium the stars contain. Higher metallicity tends to favor planet formation because you have more solid material to build rocky cores and more heavy elements to form complex molecules. The stars in this galaxy, especially in the central regions, are generally metal-rich. That's because it's old and massive. Many generations of stars have lived and died there, blowing heavy elements into the gas, which then form new stars. So on the ingredient side, this galaxy is not poor. It has had a long time to enrich itself. But there's a flip side. These stars are not just metal-rich, they're also old. Stellar population models suggest that many of them are several billion years older than the Sun. That means if planetary systems formed early around those stars, any potential biospheres would have had a head start of billions of years compared to Earth. If life ever did emerge somewhere in this galaxy, it had more time than we've had to evolve, change, and maybe die out again. You can frame it simply. The chemical ingredients for planets are there, and the clock has been ticking for a very long time. The environment, though, is not the same everywhere. Near the core, especially close to that ultramassive black hole, conditions can be harsh. Active phases of the black hole drive jets and outflows, flood the region with high-energy radiation, and stir up gas on huge scales. If your planet happens to orbit a star very close to the center, it might see frequent bursts of high-energy particles and radiation events. Those can strip atmospheres, trigger intense radiation doses on planetary surfaces, and in extreme cases, sterilize exposed life. On the other hand, high-energy environments also drive unusual chemistry in gas clouds and atmospheres, potentially creating complex organic molecules. So near the core, the story is not simply good or bad, it's more like high-risk, high-drama. Farther out, the picture changes. In the outer halo of this galaxy and in the intra-cluster light, stars are much more spread out. A single star might drift through a region where the nearest bright neighbor is far away, and the background sky is faint. Planets out there would orbit in a quieter, darker environment. The night sky from such a world might show fewer bright stars, but more of a smooth, faint glow from the distant central regions. The tidal forces on individual solar systems would be small, and major disruptive events from the central black hole would be weaker. It would feel more isolated, more lonely, but also more stable over long times. You can think of the galaxy as offering a huge menu of environments: crowded central regions with dense star fields and strong radiation fields, intermediate zones with lots of neighboring stars but less core activity, and outer halo zones where stars are sparsely distributed and the sky is dim. Each of those environments shapes the long-term evolution of planetary systems in different ways. In the core, close encounters between stars might be more common. In the halo, they might be extremely rare. In the middle, conditions might be somewhere between what you see in the Milky Way's inner disk and outer halo. Now, here's the reality check you need to hold on to while you think about all these possibilities. At a distance of around 1 billion light-years, we have zero direct observational data on planets in this galaxy. We have not detected a single exoplanet there. We can't. Our current methods rely on tiny dips in starlight, small shifts in stellar spectra, or direct images of planets around nearby stars. All of those techniques are limited to our own galaxy and its immediate neighborhood. For something this far away, the stars blur together into a smooth light profile, and individual planetary systems are completely lost in that glow. Everything you've just heard about planets in this galaxy is based on a chain of reasoning. We know planets are common around stars here. We know this galaxy has a lot of stars. We know many of them are metal-rich and old. We know different parts of the galaxy have different radiation and density environments. From that, you infer that there should be huge numbers of planets in many different conditions, even if we can't see any of them directly. That gap between hard numbers, star counts, metallicities, ages, and the total lack of direct data about actual worlds there is part of why this system feels so overwhelming. On one side, you have cold, solid stats: 100 trillion stars, billions of years of evolution, high metallicity, massive halo, ultramassive black hole. On the other side, you have complete observational silence about the specific planets that might orbit those stars. You don't know how many are rocky, how many have atmospheres, how many are in habitable zones, or whether any of them have ever hosted life. You just know that the universe has had more than enough time and material inside this galaxy to try out every possible configuration of worlds, many times over. And that leads to the next big issue. If there's that much gas and dark matter and that many stars tied up in this system, and if the central black hole is actively pushing back on the gas and starving new star formation, then how exactly does a galaxy like this shut itself down and stay quenched? What is the mechanism that keeps this giant from lighting up again with new stars, even though it's sitting in a sea of gas that should, in theory, be cooling and falling in? How do you shut down a galaxy that's sitting in the middle of a huge reservoir of gas that should, in theory, keep making stars forever? That's the key problem here, and the answer sits in X-rays, not invisible light. When astronomers point X-ray telescopes like Chandra at Abell 2029, they don't just see a few bright points, they see a huge smooth glow. That glow is gas heated to something like 10 to 100 million degrees Kelvin, stretched out well beyond this galaxy and filling much of the central cluster. The total mass in that hot gas is larger than the mass in all the stars in the cluster combined. So right away, you know something important. Most of the normal, non-dark matter in this system is not in stars. It's in this blisteringly hot atmosphere. At those temperatures, the gas is fully ionized plasma. It emits X-rays as electrons interact with ions, and as ions undergo line emission from heavy elements like iron and silicon. On paper, if you leave this hot gas alone in a deep gravitational well, it should slowly radiate away its energy, cool down, and start sinking toward the center. As it cools, parts of it should condense, form cold clouds, and eventually make new stars in the central galaxy. That predicted steady inward flow of cooling gas is what older models called a cooling flow. In a cluster as massive as Abell 2029, you'd expect a strong cooling flow with tens or hundreds of solar masses of gas per year dropping into the core. But when Chandra and other modern X-ray observatories measured this cluster in detail, that is not what they saw. The gas is hot, bright, and extended, but the signatures of strong cooling, big amounts of cooler X-ray gas, strong central star formation, and huge piles of cooled gas in the center are missing or very weak. Star formation in this galaxy is basically shut down compared to what a classic cooling flow model would predict. The expected torrent of gas falling in is not there. So something is putting energy back into the gas over and over to keep it hot and to stop it from collapsing. The leading explanation is feedback from the central black hole. When the black hole in this galaxy goes through an active phase, it doesn't just quietly swallow gas. As material spirals in, the inner accretion disk heats up and launches jets and outflows. Those jets punch into the surrounding intercluster medium and inflate bubbles or cavities in the hot gas. In X-ray images of many clusters, you literally see darker holes or depressions in the X-ray brightness where radiolobes from the active nucleus have pushed the gas aside. Even when those specific cavities are subtle in Abell 2029, the energy budget still points the same way. Repeated outbursts from the central engine are the only realistic way to keep that much gas this hot for this long. Think of it like a crude thermostat. As gas in the cluster core starts to cool and drift inward, the black hole gets more fuel. It brightens as an active galactic nucleus, launches stronger jets and winds, and dumps more energy into the intercluster medium. That extra heating slows down the cooling and the inflow. As the fuel supply drops, the AGN activity decreases again. It's not a perfect on-off switch, but over long times, this back and forth keeps the gas in a rough balance, hot enough that it doesn't collapse quickly, but not so violently stirred that it leaves the cluster. The net result for this galaxy is simple. The gas that could have become new stars is locked up in a hot X-ray bright halo instead. There's another piece of information hidden in that X-ray light, the chemical composition. When you split the X-ray spectrum for the gas in Abell 2029, you see emission lines for heavy elements like iron, silicon, and sulfur. The strength of those lines relative to the continuum tells you how enriched the gas is. In this cluster, you see a steep abundance gradient. The gas near the center, around this galaxy, has higher metallicity than the gas farther out. That pattern tells you that the stars in this central galaxy have been enriching the surrounding gas for billions of years. Supernovae in this galaxy's old stellar population have exploded, dumped heavy elements into the intercluster medium, and those metals have stayed preferentially concentrated near the core. So the X-ray gas is not just hot. It's chemically processed. It carries the imprint of countless supernovae that went off when this galaxy was younger and more actively forming stars. Over time, that enrichment propagates outward, but the strongest signal remains near the center, right where the deepest part of the potential well and the most massive galaxies sit. That alignment, central galaxy, central black hole, metal-rich hot gas, is not an accident. It's the fossil record of how energy and matter have cycled through this system over most of cosmic history. What does all of this mean for galaxy evolution in practical terms? It means this galaxy is not just passively sitting in the middle of its cluster. Through its black hole, it's actively controlling the temperature and state of a gas reservoir that holds more mass than all the cluster stars. By pumping energy into that gas, it prevents large amounts of it from cooling and forming new stars, not only in the central galaxy, but also in other galaxies that might otherwise accrete some of that gas. In other words, feedback from one ultramassive black hole is helping decide whether hundreds of neighboring galaxies stay quenched or get a fresh burst of star-forming fuel. For theorists, this galaxy and its cluster are a crucial test. Any realistic model of how galaxies grow in a universe dominated by dark matter and dark energy has to include feedback from stars and black holes. But getting the balance right is hard. If feedback is too weak, clusters end up with strong cooling flows and central galaxies that are far too bright and star-forming compared to what we see. If feedback is too strong or too efficient, you end up blowing out too much gas and starving galaxies too early. This system, with its massive, quenched central galaxy, its hot, enriched gas, and its weak cooling, is one of the sharpest checks on whether those feedback recipes are even close to right. So the stakes are big. This galaxy is more than an impressive statistic or a pretty image. It's a working example of how an ultramassive black hole, buried in the core of a supergiant galaxy, can reach out through energy feedback and reshape an entire cluster. It changes not just its own future, pushing itself toward that red and dead state you heard about, but also the evolution of hundreds of other galaxies locked in the same dark matter halo. And if feedback and mergers can build and then freeze a system this extreme in just 13.8 billion years, the obvious next question is, what does that tell you about how fast structures can grow in our universe, and are our standard cosmological models actually capable of building something this big, this early, without breaking something else? How do you get something this extreme in only 13.8 billion years when the universe had to build everything else at the same time? To answer that, you have to zoom out from one galaxy and talk about how structure forms in the standard cosmology picture, the one called lambda cold dark matter. In that model, small dark matter clumps form first. They merge into bigger halos, those merge into even bigger ones, and over billions of years you build up a hierarchy, little halos inside bigger halos inside cluster-scale halos. This galaxy sits right at the bottom of one of those cluster-scale dark matter wells. From very early times, its region of space was slightly denser than average. That extra density made gravity stronger there, so matter fell in faster. Small halos merged into larger ones, gas collected, and the first generations of galaxies lit up, and instead of just forming a Milky Way-sized object and stopping, the process kept going. For billions of years, this region stayed at the nexus of that merging, pulling in group after group of galaxies and folding them into the growing cluster. The central galaxy rode that wave from the start, always sitting near the deepest part of the potential, and that is why it ended up so big. But you don't get to 100 trillion stars and a core that huge with just a handful of collisions. Structural studies of this galaxy, plus simulations that try to reproduce similar brightest cluster galaxies, suggest a history of mergers stacked on mergers. The depleted core size and the mass deficit you heard about earlier imply many runs of black holes sink, form a binary, fling stars out. To carve out that much central mass and build up that much stellar envelope, you're looking at something like 10 major mergers with other massive galaxies, plus countless minor mergers with smaller ones. A major merger here means two galaxies with comparable mass slamming together, not a big galaxy eating a tiny dwarf. Each major event roughly doubles the stellar mass of the central system and can add another big black hole into the mix. Minor mergers keep feeding in satellites and outer halo stars. Over time, the central object grows not by slow, smooth gas infall, but by swallowing whole galaxies, grinding them up and mixing their stars into one extended body. This is exactly the growth channel that standard cosmology expects in dense cluster cores. Once you have a big central galaxy, dynamical friction pulls in massive satellites and the process feeds on itself. Now scale that up to the black hole in the center. Models of black hole growth usually start with a small seed, maybe a few tens of solar masses from a dead star or a direct collapse black hole, tens of thousands of solar masses, and then let it feed on gas, limited by radiation pressure. That limit, called the Eddington limit, sets a maximum steady growth rate. If you run that growth under typical conditions over the age of the universe, you can reach black hole masses of around 10 billion suns without too much trouble. Maybe a bit more if you give it good fuel and plenty of time. The problem is that the best estimates for the central black hole in this galaxy are not 10 billion, but tens of billions of solar masses, pushing up toward 100 billion. That suggests that something more than just steady Eddington-limited accretion from a gas disk has been happening. You probably need at least two extra ingredients. One is mergers of already massive black holes after their host galaxies merge. Each time two big galaxies combine, their central black holes sync together and can eventually coalesce into a single, more massive one, stepping the mass up by large jumps instead of just slow feeding. The other possible ingredients are periods of super Eddington accretion, where for a while the black hole manages to pull in gas faster than the standard limit would allow, perhaps because of special disk geometries or very dense gas flows. Either way, to get to the mass range people are inferring here, you're running this growth pathway right up against the edge of what our models consider plausible. You're stacking early formation in a dense region, multiple major mergers, black hole coalescences, and maybe unusually efficient accretion. This is why objects like this galaxy are used as stress tests for theories of black hole evolution. If your model of black hole growth cannot produce a system like this without unrealistic assumptions, that model has a problem. The same kind of tension shows up in galaxy formation models. Semi-analytic models and large cosmological simulations often have trouble making brightest cluster galaxies that are as massive and extended as what we see, without breaking something else. If you pump in more gas or let star formation run too efficiently in the cluster core to build a huge central galaxy, you end up overproducing stars compared to the cosmic average. If you crank up feedback to stop that, you risk making the central galaxy too small or too faint. Getting the right combination of cluster mass, central galaxy size, outer halo, intra-cluster light, and quench star formation is hard. This galaxy sits right where these models are most fragile. Its star count, core size, halo extent, and black hole mass all live in regimes where small changes in the physics, how gas cools, how feedback couples to the intra-cluster medium, how often mergers happen, how fast black holes grow, can make a big difference. If a simulation can match this system while also matching normal galaxies like the Milky Way and more modest clusters, that's a strong sign that its underlying physics is on the right track. If it fails, that tells you the model is missing something about how the most massive structures assemble. Think of the buildup timeline in simple terms. Very early on, small dark matter halos form and host the first galaxies. Those halos fall together and build up a big cluster halo. Near the center of that growing halo, gas cools and forms stars rapidly, building a proto-brightest cluster galaxy. As time goes on, groups of galaxies fall in, bringing their own central galaxies and black holes. Major mergers inflate the size of the central galaxy and carve out its core. Minor mergers and tidal stripping pump up its halo and the intra-cluster light. All along, the central black hole is growing and feeding back energy into the gas, eventually quenching further star formation. By the time you get to a universe that's 12 to 13 billion years old, you end up with what you see in this system, a massive dark matter halo on cluster scales, a central galaxy with 100 trillion stars and a multi-million light-year halo, a depleted core that's larger than many galaxies, and an ultramassive black hole hovering near theoretical limits. This is exactly the kind of object you look at and ask, does our universe model really handle the extremes? So when you hear this galaxy described as one of the largest galaxies we know, it's not just hype. In the context of structure formation, it really is like a final boss. If your version of lambda cold dark matter can build this, quench it, and still match everything else we see, from dwarf galaxies up to typical clusters, then your picture of the universe is in decent shape. If not, then systems like this are where the cracks will show first. And once you've pushed the growth history this far, another question pops up. Is this truly the top of the ladder, or have we just happened to study this one really well? Are there other galaxies and cluster cores out there that are as big or bigger, but harder to measure? And does that mean even our idea of biggest galaxy is more about what we've managed to observe than what actually exists? How sure can you really be that this is the biggest galaxy, and not just the one we've poked and prodded the most? That's the first thing you should question, because once you look around, you see other monsters in the same weight class. Astronomers have found several brightest cluster galaxies with extreme envelopes and intra-cluster light, very similar in spirit to this galaxy. The central galaxy in Abell 1413, for example, is a supergiant elliptical with a huge low-surface brightness envelope and very large effective radius. It's been flagged for decades as one of the most luminous and extended CD galaxies known, with deep imaging showing a titanic outer halo. Another case is ESO 306-17, a fossil group giant elliptical. It's roughly 1 million light-years in diameter based on the region containing most of its B-band light, and some discussions suggest an even more extended influence, likely built by cannibalizing its former group companions. NGC 6166 in the Abell 2199 cluster is another classic central CD, a supermassive elliptical with a diffuse halo that blends smoothly into the intra-cluster medium, with globular clusters and stars traceable out to hundreds of thousands of light years. Here's the key point. When you define size using certain isophotal diameters, that standard D25 rule of where does the light drop below a set level, some of these brightest cluster galaxies can match or even beat this galaxy. Even the IC1101 page itself notes that other galaxies, including the BCG in Abell 1413 and ESO 306-17, have larger diameters under that strict surface brightness definition. So if you insist on one single number for how wide is it, the ranking is not clean, and this galaxy does not always come out on top. That leads straight into the next complication. What do you mean by structure of galactic origin in the first place? If you count not just stars and halos, but also jets and radio lobes, you get a very different leaderboard. Take Alcyone. It's a giant radio galaxy whose radio lobes, powered by jets from its central black hole, span about 5 megaparsecs, roughly 16 million light-years. The host galaxy itself is not especially extreme in size or mass, but the radio structure is enormous, one of the largest known of any galaxy. You could honestly say it's among the largest galactic origin structures in the universe, but that's talking about jets, not the stellar body. So depending on whether you care about stars, faint halo light, or radio ejecta, you end up with totally different answers to what is the largest galactic-like thing. Once you see that, you have to ask a more uncomfortable question. Are we giving this galaxy the crown because it's truly unique, or because we happen to have unusually good data on it? Abell 1413, the cluster it sits in, has been targeted by multiple big facilities: deep optical imaging, Hubble snapshots of the core, detailed Chandra X-ray observations, and weak lensing studies. Abell 1413 has also had deep optical and Hubble work, revealing its extreme BCG and lensed arcs, but not every cluster in the sky has that level of coverage. There are many rich clusters at similar or higher redshifts with only shallow imaging and limited spectroscopy. If a BCG out there has a halo and intra-cluster light as extended as this galaxy, or even more so, but nobody has pushed the observations down to very low surface brightness, then on paper it will look smaller, even if physically it isn't. So why does this galaxy still end up as the go-to example in videos, articles, and even research papers when people talk about largest galaxy? Because it has the full package, and that package is unusually well documented. It has one of the largest depleted cores ever measured, with a break radius around 13,700 light-years and a huge stellar mass deficit. It has an extended halo and intra-cluster envelope detectable to something like 2 million light-years from the center. It has strong evidence for an ultramassive black hole, possibly tens of billions of solar masses, and it lives in a cluster that has been mapped in X-rays, lensing, and dynamics, so its dark matter halo and environment are relatively well constrained. Put that together and you get a system that is not just big, but big in multiple well-measured ways. In other words, this galaxy is famous not just because of a single headline number, it's famous because every time you measure a new property, core size, star count, halo extent, black hole mass, intra-cluster light, the result lands near the extreme end of what you've seen anywhere else. Other BCGs might win on one axis, like radio lobe size or isophotal diameter under a specific definition, but this galaxy is consistently near the top in several categories at once, and that's why it's the textbook extreme people keep coming back to. So for you as a viewer, what should you actually take away from this? The important message is not, this is absolutely the largest galaxy in the universe, full stop. Observationally, that claim is too strong. And it's very likely that as we push deeper in surface brightness and find more distant clusters, we'll uncover more contenders. The real takeaway is that the universe is fully capable of assembling galaxies so massive, so extended, and so dominated by cluster-scale physics that our everyday language about size and diameter starts to break down. Once you bring in objects like this galaxy, Abell 1413's BCG, ESO 30617, NGC 6166, and radio giants like Alcyonus, the simple idea of biggest galaxy stops being a clean ranking and turns into a set of different, overlapping extremes. Largest in stars, largest in halo, largest in radio jets, largest depleted core. And as you keep chasing those extremes, one last question naturally appears. If even our size labels are starting to fail, what does the long-term future of a system like this actually look like? How does a galaxy this big age, keep merging, and eventually fade as a universe moves toward its far future? How does something this big actually end? Does it even have an ending in any normal sense? Or does it just keep grinding on long after everything familiar to you is gone? To wrap this up, you have to stop thinking in millions or even billions of years and start thinking in lengths of time where whole galaxies live, merge, fade, and still aren't done. First, look at what happens over the next few billion to maybe a few tens of billions of years. Abell 2029 is not frozen. More galaxies are still falling toward the cluster core along filaments of dark matter. As they come in, they feel the tidal field of the cluster and of this galaxy. Their outer stars and gas get stripped first, smeared out into long streams that eventually blend into the intercluster light. The denser cores of some of those galaxies survive long enough to plunge deeper toward the center, where dynamical friction slowly drags them in and they merge into the main body or the inner halo. Piece by piece, the central structure gets more massive and more diffuse at the same time. The bright, sharp outlines blur, the halo thickens, and the difference between galaxy and cluster envelope gets even harder to define. So here's your first key point about its fate. Growth does not stop just because a galaxy is already huge. As long as a cluster keeps pulling in material, this galaxy will keep eating. The rate will drop over time as the universe expands and as the cluster cleans out its surroundings, but the direction is one way. More stars added to the halo, more intra-cluster light, more mass at the center. On galaxy scales, the cannibalism never really reverses. At the same time, star formation keeps sliding toward zero. Right now, this galaxy already has very little cold gas compared to its mass. The gas you see in X-rays is hot, thin, and spread out, hard to cool and collapse. Feedback from the central black hole and from the cluster environment keeps that gas stirred and heated. Over the next few billion years, whatever small amount of residual star formation remains will fade. No large new disks will form, no big blue starbursts will light up the core. The stars you see now, plus a small trickle of late arrivals from little gas-rich satellites, are basically all it's ever going to get. So what does the galaxy look like as that process continues? The most massive stars are already gone. Intermediate mass stars, like the Sun, will swell into red giants, shed their outer layers, and leave behind white dwarfs. Some massive stars and infalling satellites will still explode as supernovae, but those become less and less common. Over tens of billions of years, the population shifts more and more toward long-lived red dwarfs and remnants, white dwarfs, neutron stars, and stellar mass black holes. The light of the galaxy turns progressively redder and fainter, carried mostly by small, dim stars that can burn for hundreds of billions of years. Then you stretch the clock again, this time to trillions of years. On those timescales, gravity reshapes the inner structure in a different way. Massive objects, heavy stars, stellar mass black holes, compact remnant cores, slowly lose orbital energy and sink toward the center through dynamical friction. In a galaxy and cluster this big, that process is slow, but you now have ridiculous amounts of time to work with. Over trillions of years, a significant fraction of the most massive bound objects will wander inward, feeding the already enormous central black hole. Some will fall straight in. Others will interact in close three-body encounters, being flung outward while the survivors sink deeper. In that far future, this galaxy is moving toward a state where one single black hole could dominate the binding energy of the whole system. You end up with a central ultramassive black hole, potentially heavier than it is now by orders of magnitude, sitting at the bottom of a much more diffuse, much dimmer stellar halo. The remaining stars orbit it the way comets orbit the sun now, as leftovers in a system where most of the action has already happened. In extreme scenarios, especially if multiple black holes have merged in the center, gravitational wave emission can even eject some remnant, but the bulk stays locked in that central well. If you push the timeline even farther, out to ridiculous numbers like 10 to the 15th or 10 to the 20th years, you enter what cosmologists call the degenerate era. By then, essentially all normal stars that can burn have done so. The galaxy is no longer made of shining main-sequence stars. It's a fog of white dwarfs, neutron stars, stellar mass black holes, and that central ultramassive black hole, plus cold, dim brown dwarfs that never quite made it to full star status. Occasional rare events, like the merger of two white dwarfs or the tidal disruption of a star by the central black hole, will still release bursts of light, but those are flashes in an otherwise dark environment. On top of that, dark energy is still at work, accelerating the expansion of the universe. Over very long times, more and more distant structures cross beyond each other's cosmic horizons. The cluster around this galaxy, and eventually even just the dark matter halo and its bound contents, become effectively island universes. Light from beyond a certain radius will never reach them again. From the point of view of any observer still somehow around in that future, their observable universe has shrunk to the local bound structure and nothing more. So, ending is not really a good word for what happens to a galaxy like this. The Abell 2029 cluster, plus this galaxy at its core, becomes a single gravitationally bound patch of matter drifting in an otherwise empty-looking cosmos. Over ridiculous timescales, even many of the bound remnants can be scattered out by rare gravitational encounters, leaving a smaller and smaller fraction actually tied to the core. Eventually, you're left with a dark matter halo, a thinning sprinkling of cold stellar remnants, and one or a few supermassive or ultramassive black holes in the center. So, in the longest view, the fate of this galaxy is not an explosion, not some dramatic end, but a slow fade. It keeps merging and growing in mass for a while, but its light output drops as its stars age. Its central black hole keeps eating, but each meal is less dramatic compared to the whole. Its cluster becomes more dynamically quiet as infall slows and outside structures drop out of causal contact. The system goes from an overgrown, overbright central galaxy surrounded by thousands of companions to a large but lonely island of dark matter and dead stars in a universe that, on the largest scales, has gone almost completely dark. And here's where you bring it back to you. On human scales, on planetary scales, even on the lifetime of the sun, this galaxy is effectively eternal. It will be there long before the Milky Way and Andromeda have merged, long before the sun has turned into a white dwarf, long before Earth, as a habitable world, is gone. The structure built in the core of Abell 2029 will outlive your galaxy, your star, and anything like the current night sky you know. So when you hear that IC 1101 is bigger than your imagination, don't just think about its size in light years or its 100 trillion stars. Think about how far it stretches in time. It's an object that keeps growing, keeps fading, and keeps existing on timescales where everything familiar to you, the Milky Way, the sun, even the part of the universe we can see today, is just a brief episode. IC 1101 is bigger than your imagination, not just in size, but in time. It outlives your galaxy, your star, and maybe even the part of the universe we can ever see. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.